by Liam Madrid, Javier Peña, Gerardo Guerrero, and Luis Alvarado.
Good morning and welcome to Barefoot Electronics final presentation. Our team is composed of Liam Madrid, Javier Peña, Gerardo Guerrero, and myself. And we built an aquaculture maintenance system. Firstly, in the presentation we'll be talking about introduction, then we will talk about the design, the system architecture, including all three modules, the budget, the results, and finally the conclusion. So AMS, also known as Automated Maintenance System, is an automated solution for small aquaculture farmers. It determines when oxygen and temperature levels drop below the established user limits. It provides the user with an automated oxygen and temperature readings and its proper solution, using valves and air pumps. It provides the user with freedom to control the variables or parameters, and it gives a backup energy system. This prototype gives the opportunity to boost aquaculture here in Puerto Rico, and also reduces operational costs, therefore increasing profitability.
So our main design is composed of three modules. First one is the main control system, which is the heart of the system. We have the user interface and the power supply. This is the system architecture for what we originally proposed. We have the control system. The control system contains temperature sensors and oxygen sensors. It retrieves data from the fish tank conditions, and it transfers them wirelessly to the user interface, which is in the user's house in the case of our client. The user can see temperature and oxygen values, and it can control them from his house. This module is powered by 4 AA batteries, and the control system is powered directly from the grid, and this battery right here is for a backup energy system which can last for a little bit more than 4 hours. This is the user interface module that goes inside the user's house. We have an LCD display. This is where the user can see the real-time oxygen and temperature values. The black button is used for on-accept. The red buttons, the user can control the variables through those buttons. We have the two LEDs. The green one is for when the system is regulating, and the red one is for when the system detects any failures, along with the buzzer, which goes on when it finds any system failure. It communicates wirelessly with the control system and is, as I mentioned before, powered by 4 AA batteries. The control system. It controls the cold valve, the heater valve, and the drain valve through 3 relays. We also have in this module the oxygen sensor and temperature sensor, and it communicates wirelessly to the user interface box.
So here we have the system architecture. We have this set up at the Finca Alzamora here in the university. As you can see here, this box right here with the cables connected is the control system. It has both of the sensors that go inside the fish tank, and with this wires, it's connected to the power, and it also controls the water valves. Here we have 2 water tanks. One has hot water, and the other one has cold water. And depending on whether the temperature is low or high, we will inject either cold or hot water. Here we have the user interface. We put it in there, but it doesn't necessarily need to be in the tank. It could be in the user's house. This has a range of about 30 meters, so we can move it around and put it in some place that the user can be more accessible to it. Here we have the power supply, which powers the control system, and also powers up the air pump we have set up. Whenever the oxygen level goes lower than the user wants to, this air pump is going to turn on and re-oxygenate the water. We also have the battery right here. It's not so much visible with the light, but the battery is up to 4 hours and of continuous sensing and regulation. So here's our budget. Basically, what we originally had set up for a budget was 22,000, mainly 23,000. We actually went overhead because one of our parts got damaged, so we needed to order a new one. So that's put us up $60 over, and the prototype costs $682, and it cost us $750 because of the damaged part. Our overhead expenses were resulted as 846 when we had 700 and 907. So it's kind of the same thing. The only thing is those $60. For our market, our main market is here in Mexico, local aquaculture farmers, and our main, the other components that we have compared ourselves to is the IQ SensorNet 182 and Aquaculture 749, and these two devices are specifically sensing, only sensing. Our device provides the regulation part that these other devices do not provide. So, next slide, please. For our progress, we completed everything 100%. We first designed each one of the modules separately. We tested each one of the modules separately. Also made sure that the software was being complied by the hardware. It was interfacing well. And after that, we put it all together, and then we also tested the implementation of all this. So yeah, that's.
In conclusion, all of the digital workflow process for the prototype were successfully completed. First, we were able to allow the user to define the limits where the prototype should maintain the oxygen and temperature levels of the water. Then, these values were displayed on an LCD located at the user interface for the user to have track of them. The system also is capable to detect when the water needs regulation and inform the user that an action is going to be taken, and if this water condition reach limits imposed by the own system, he sends an alarm to inform the user that the own system cannot solve the situation. The system makes use of air pumps and water valves in an efficient way to control the water temperature and the water oxygen at the same time, and taking into account that these two variables are dependent between each other. Also, the backup system is capable to supply the system with enough energy to properly function for about 4 hours. Although this value depends on the battery capacity and the use of the regulation system. For future works, we want to add solar panels to the system to reduce the operational cost due to electric consumption, and reduce this electric consumption is one of the most important costs on the production of this type of systems. We want to add more parameters to control that are important in aquaculture systems, such as the conductivity and the pH of the water. We are trying to develop a system to collect the data of the water condition for further studies and development of the system, and we want to implement it in a real and complete aquaculture environment. Also, we have in mind to design an automated system to dispense food to the fish in order to reduce the user interaction with the system. Well, thank you for your attention. Any questions?
Mencionaron que el mercado es de Puerto Rico nada más. ¿Por qué? ¿Por qué no puede ser en Florida o en California o en algún otro sitio así?
Okay, can I answer in Spanish? Spanish? Is it okay? Okay. Mayormente escogimos el mercado aquí localmente en Puerto Rico porque nuestro producto solamente tuvimos la referencia de visitar fincas que están aquí en Puerto Rico. Por ejemplo, fuimos a Lajas, estuvimos trabajando muy cercanamente a Patrick aquí en la finca El Zamora, y pues mayormente ese es nuestro marco de referencia. Sí pudiéramos expandirnos a Estados Unidos, pero estamos buscando un market mayormente de pequeños agricultores que se encuentran en el área, que el revenue anual es menos de $250,000. Las grandes fincas de agricultura, ellos tienen un equipo extremadamente avanzado, pues, porque son bien grandes. Entonces el equipo de nosotros, pues, a lo mejor no les es tan necesario a ellos. Sin embargo, nuestro equipo, para un agricultor que está comenzando a trabajar, que está empezando con su finca, es excelente. Y esto dicho desde el punto de vista también que buscamos referencias con nuestro cliente en Laja, el señor Daniel McGee y Patrick, nos dijeron que era un excelente producto para una finca de agricultura no muy grande, pequeña, que tenga ese range.
Y además a eso es para ayudar a la acuacultura aquí en Puerto Rico. Aparte, se están haciendo cambios para el café, para mejorar la agricultura y volver a lo que teníamos antes. Pues esto es un punto importante para ese proceso.
¿Cuánto tendrían que vender para sacarle ganancia al producto? ¿Cuánto tendrían que vender?
Bueno, aproximadamente podríamos vender, para sacarle ganancia al producto, tendríamos que vender alrededor de 50 unidades promedio, más o menos. Como a promedio, como unas 50 unidades, siendo un cálculo estimado. ¿Sí?
¿A qué precio?
Lo venderíamos, por ejemplo, a $1,000 cada unidad.
¿Eso te alcanza para el salario tuyo de un año?
Pues, no, fíjate, no necesariamente me alcance para el salario que por lo menos el que propusimos en nuestro trabajo. Bueno. Pues, entonces, en cuanto a ese punto de vista de usted, pues tendríamos que vender un poquito más por encima. Sí. Yo sé.
Maida, no se oye.
I saw that the power supply was lying around in the system next to it. So I'm wondering if the system works when it's raining.
El power supply no necesita estar exactamente al lado del sistema. Lo que tiene son unos adapters que se pueden conectar a través de cables, que uno los coloca con la distancia que requieran. Puede estar en un lugar apartado del sistema y todavía funcionar bien. O sea que sí podría trabajar bajo condiciones de lluvia.
Vuelves a Future World. ¿Qué quieres decir con el penúltimo?
Bueno, lo que sucede es que el prototipo que nosotros montamos está diseñado para controlar un solo tanque de peces. En realidad en los sistemas de acuicultura se manejan cientos o decenas de tanques al mismo tiempo. Entonces por lo menos lo que es la bomba y las válvulas de agua se tendrían que cambiar las consideraciones de tamaño para poder adaptarse a controlar una mayor cantidad de tanques. Entonces por lo tanto nosotros pensamos que el prototipo que nosotros montamos funciona en un ambiente de acuicultura, pero no en uno real como se estaría trabajando en la finca directamente. Nosotros estamos trabajando en una finca, pero el sistema que tenemos es pequeño comparado con el que tiene el agricultor con el que nosotros estamos trabajando.
¿Funcionaría igual que en una charca?
Sí puede funcionar en una charca, aunque hay que tener en cuenta que la charca es más grande y también puede filtrar el agua, así que el sistema tendría que estar utilizándose más tiempo que el que se estaría utilizando en el tanque de peces, así que la potencia que va a consumir va a ser mayor y hay que tomar eso en consideración para el sistema de energía.